All right, so we are going to get started up again, and we're going to start with a pair of topics that are related to each other, and that's the step 0 that I breezed over before, and that's how the client even knows how to talk to the auth server and vice versa. This is registration and discovery. So we've already talked about registration a little bit. The protocol itself turns out to be really pretty simple. The client shows up at the auth server and says, this is everything you need to know about me. This is my display name. This is the redirect URI I'm going to use. These are the grant types that I can do. These are the scopes that I want. And it sends all of that to the auth server, and the auth server says, OK, you're a new instance of a client, and I'm going to know you by all of this, and I'm going to issue you a client identifier that's unique to you. And maybe I'm going to issue you a client secret. Or maybe you registered one of your keys with me that you're going to use instead of a client secret, or a certificate thumbprint or anything like that. Any of that information that we normally have about the client application, we're going to have as part of that registration process. That gets tied together. So the client, from that point, just moves on like a normal OAuth client. It's going to go do everything. Whatever grant type it's doing, it's going to send its redirects, talk to the token endpoint, all that fun stuff. So this begs an interesting question, though. How do I trust somebody that is coming and doing a dynamic registration? We have a function in the dynamic registration protocol that allows you to have a signed assertion from a third party that allows you to do this registration. And more than that, it allows you to do this registration with specific parameters. So the client is not allowed to override anything that is in this signed statement. So if the signed statement says, this is your display name, the client can't say, oh, no, really, I'm this other app. If it says, this is your redirect URI, the client can't say, oh, no, really, I'm this other thing, right? So it presents that alongside any other attributes that could vary, and it still gets a unique ID and, usually, a unique secret. So we do this for a couple of different reasons. One of the most common is so that I can track many instances of a piece of client software. Before when I was saying that maybe I had 1 million copies of an app on 1 million different phones, if I'm managing the authorization server and they've all dynamically registered, I would really like to be able to, in my admin console, say like, OK, this version of this application, pull that now. Because we know it's doing something wrong, or it looks like it's doing something weird. Like, just pull that right now. The software statement with dynamic registration lets us tie all of those together, because otherwise, it's just the client self-asserting that this is the application it is being. Right? The other thing that it allows us to do is to allow registration across different security domains. So I can issue my applications a software statement that they can then use to go talk to your authorization server in a different security domain and register. This is in use today between mobile phone data carriers. So a T-Mobile branded application will get something like this, and it will be able to talk to and dynamically register to a remote server with Verizon to be able to speak to it. This is a profile called the Moderna profile in OpenID Connect. Now, that's how the server knows about the client. How does the client even know what server to talk to? So this is sort of the inverse of that same problem. And we've got a process that we can use to find the issuer URL, sort of the root URL of the server. And there is a protocol called WebFinger, which we unfortunately don't really have time to get into now, that maps something that looks like an email address to something that looks like a URL that you can actually do an HTTP GET on. That gets us this thing called an issuer URL. But how do we bridge from that to all of the server information? Well, what we're going to do is we're going to take our server, and then we're going to tack on what's called a well-known URL. And this, in particular, is from OpenID Connect, which is an identity protocol built on top of OAuth. And that gets sent by the client, and you get back a JSON document with all of the configuration information that you need to run. So one of the cool things about this is that it allows you to very quickly start up a client talking to an authorization server without having to type all of these different bits of information in there. So you give the client one URL, it goes and fetches this document, and everything kind of falls out from there. Interestingly, these days, these configuration documents are getting really, really, really big because of all of the different optional modules and add-ons to OAuth and OpenID Connect allow you to go in a lot of different directions here. So I am going to take a quick, oh, come on, where is it? Oh, hang on. Nope, wrong one. Okay. Thank you, Windows. You make no sense. All right. So people were asking before what I do as an API to manage and deal with, like, how do I know what a token's good for, right? Get this question a lot. So OAuth tokens are opaque, but they're opaque to the client itself. So the protected resource needs to know what the token's good for, might care about who issued the token. If you've got an API that talks to multiple authorization servers across domains, it's not a common deployment pattern, but it's there. And importantly, is the token even still valid? So traditionally, you've got 3 different ways to do this. In OAuth 1, and really the world where OAuth 2 started, the AS, the authorization server and resource server were the same device. They were the same box. And that meant that when the authorization server issued a token, it wrote a line into a database, into the tokens table. And then when the resource server got in a token, it would just go look up in that same database table to see, is that token in there, and what does it mean? This is one of the main reasons that OAuth 2 does not specify how the RS figures out what the token is, because far and away at the time, this was how things were deployed. Microservices weren't really a thing. Cloud deployments weren't really a thing. Wide distributed data systems weren't really a thing unless you were Google. But for the most part, nobody else was really doing it at that time. These days, what does computer even mean? Right? If you're running a server, it could be an AWS Lambda function, and like we're getting to the theoretical limits of what a computer even means. No longer are we talking about a piece of software, a single piece of software running on a single device anymore, right? So in those cases, you could pack the information into the token itself. We talked about JOTs before. If we have time, we'll get into what JOTs actually look like and how they work. Or you could query the AS, because the resource server can get in an access token and basically stop and say, hold up, I need an adult. I need somebody to tell me what this token is good for. And it does that by doing a really simple lookup protocol. The auth server responds with a JSON object that says, always says, is this token currently active? And may give you other information if the token is active. Because that's ultimately what the resource server cares about. Is the token good? And specifically, is it good for what's being asked? This is token introspection, RFC 7662. Yes? Oh, the signed introspection response? Okay, so there is a draft running through the IETF right now for getting a message level signature on an introspection response. If you're asking me when the IETF will decide to publish that, I have no idea. These things take ages. Introspection was something that, like, the spec basically didn't change from 2011 onward until it was finally published in 2015, I think. It was a long time. And yeah, the system is dark and mysterious and full of terror. Sorry. It's far-ish along in the process, but who knows? The biggest thing about introspection is that there are some big trade-offs. It does require the RS to carry its own set of credentials to identify it, because you don't want necessarily anybody to be able to say, like, oh, here's a token, what's it good for? You don't want an attacker to be able to grab a token and then figure out every place that it's good for and what it can be used for. You also don't necessarily want a resource server to be able to show up with an access token that could be used on multiple resource servers and figure out other rights and accesses that are associated with it. But if your resource server can identify itself, well, then the authorization server can then say, oh, I will tell you the bits that you care about. Maybe I know that you don't need to know the user's ID. You just need to know the set of scopes. Maybe you only need to know some of the scopes and not all of them. I don't want to leak that information if I don't have to. But that is another layer of management. It does require more network round trips and more network traffic. The upside here is that if you think about how our deployments tend to work, our auth server and resource server, even though they're not in the same box today, they're usually topographically relatively close to each other. Because they're going to be deployed in sort of the same cloud, or you can have some very fast connections between these. So the trade-off of being able to do that lookup is relatively quick, as opposed to the client's connection into the API, which is probably going out over the wide public internet, and heaven knows however many TLS terminators and VPNs and everything else between that endpoint and the actual API. So that's where your big delays are going to be happening, not really between the AS and RS. So that's manageable. The other thing that helps the introspection protocol is that you can cache the results. Because if somebody's coming at me with an access token, and I go look up what it's good for, and somebody shows up from the same remote IP address with the same access token to the same API 1 second later, what are the chances that the answer is going to have changed? Pretty slim. So it's safe and reasonable to cache this for a lot of things. But now I get to choose whether I trust the cache or whether I look things up. Because maybe you asked about demographic information, and now you're asking for sensitive medical records. Okay, no, I'm going to go look up that token again, because I really, really, really want to make sure that that's still real. Or maybe you asked for my transaction history on my bank, and you paged through like 3 or 4 pages of my transaction history. I expect you to do that with my API. That makes sense. And then you send me the thing that says, transfer $1 million to this Cayman Islands account. I'm going to be like, you know what? I'm going to double check that access token before I do that. You have that choice, but making that choice is very contextual, and there's not an easy way to go about it. And this brings me to one of my favorite jokes in all of computer science, that there are really only 2 hard problems in computer science. Naming things, it's very hard, cache consistency, and off by 1 errors. So, now that I have an access token, maybe I've decided that I don't need it anymore. And the client, this is not a user going and revoking an access token. This is the client software saying, like, you know what? If anybody shows up with this access token, it's not me, because I'm getting rid of it. This is a very simple extension protocol. It's a new endpoint on the auth server. because maybe the user selects deauthorize my app or log out, or they uninstalled and it's a pre-uninstall hook or something like that. You can throw away access tokens that you might have sitting around. This allows good clients to clean up after themselves. And it's a really, really simple protocol. The client basically posts, and it includes the token in the body, and the server says, it deletes it if it finds it, and then it comes back and says, everything is just fine. And if the server can't find the access token, it comes back and tells the client, everything is just fine. And if it finds out that that's a stolen access token for a different client, it's going to come back and tell the client, everything is just fine, while it raises a whole bunch of red flags and tells the admins in the back end. Why? Well, a lot of times when we're building out security protocols, it's really tempting to send all sorts of signaling information to the client about exactly what went wrong and how it went wrong and stuff like that, stuff that developers feel that they want. But you got to think of it in terms of not just sort of information oracle attacks, which the security wonks in the room are probably thinking like, yeah, you don't want to disclose that. More importantly, think about what the software is going to do. Well-meaning software is going to take a look at that response and say like, okay, I tried. I did my part. I threw out the token. And if it didn't work, I'm about to disappear probably anyway. I'm not going to try again. You know, I did my bit. Let's move on with the day. A malicious piece of software, if it manages to delete a valid token, you just told it, hey, your token theft worked. So go steal another token in the same way that you just did, and now you get to use it. Maybe a little bit more carefully without setting up red flags. And if it didn't work, well, that gives the attacker information about maybe your token structures. You know, maybe that token that I tried to guess didn't work. Maybe I tried to manufacture my own tokens. And, you know, it gives more information to an attacker and no useful information to a good client. Nothing actionable anyway. All right. So we are now going to take a lightning tour through the world beyond bearer tokens. All right. So everything that we've been talking about so far today are OAuth bearer tokens. And the reason is that that's pretty much the only kind of OAuth token that is out there in the real world. When we built OAuth 2, we added a field called token type with the idea that you would have a bearer token and you would have non-bearer tokens. You would have MAC access tokens. You would have other different kinds of things, right? So that means that anybody who has access to the token is allowed to use it. It's a bearer. So there are a lot of things in life that are bearer tokens. Most tickets to events are bearer tokens. Whoever holds the ticket can get in. You don't have to prove an identity. You don't have to prove possession of any secret. You don't have to know a secret code word as well. If you have the ticket, you can get in. You can hand the ticket to somebody else and now they can get in. But maybe you can't because you don't have the ticket anymore, except that these are digital systems. And when I hand something to you, I get to keep a copy of it because that's how communication works in the digital space. So this is a bit of a downside. The upside, of course, is that this is very, very simple to deploy and use. People get it. They understand it. I get this string. I put this string in an HTTP header. I'm done. Worlds better than the complex systems of the past that required clients to jump through all sorts of signing hoops and binding hoops to make things work, which they would then often get wrong and cause people to turn off all of those extra protections anyway, turning the tokens back into bearer tokens while they were pretending to not be bearer tokens. Now, this, as a bit of an aside, is what I like to call a very complicated unlocked door. So when you walk up to a door and it's got a combination lock on it, But then it has the combination to that lock on a sticky note next to the combination lock. That is an unlocked door that is pretending to be locked. Now I have, unfortunately it's not in this presentation, but I have a picture from a friend's, where her parents lived. There was a gate, it had a combination lock on it, and it had not a sticky note, but a metal plaque riveted to the fence with the code for the gate next to the padlock for the gate. This is a very hard to use unlocked door, but it makes people feel safer because it's like, at least I put a lock there, right? So while bearer tokens definitely have their downsides, there's still, you're actually locking the door. And that is a gigantic upside. That said, there are a lot of cases where people are starting to move beyond the space where bearer tokens make sense. We want to be able to prove that whoever has the bearer token is the one that is allowed to present the bearer token. So this is the proof of possession mechanism. And there have been a couple of different attempts to do this in the OAuth world. Initially, there was the MAC token specification, which allowed you to do this kind of HTTP signature. That morphed into the HTTP signing mechanism and the OAuth proof of possession architectures stuff. This has recently come up again with the DPOP. I forget what the D stands for. It's D proof of possession or something. And that's a new system that binds these tokens. But ultimately, what it boils down to is you get a two-part token. You get the actual token, which still is opaque to the client, still gets sent as is. And you get a key, which is used to sign some part of the request. Now, the mechanisms for generating and associating that key, that varies depending on which of the different proposals you're looking at. But a lot of it boils down to this notion of, I'm giving you a token and I'm giving you proof that I can use this token. Now, why do we send both? Why not just send the proof that I had a secret at some point? Well, remember, OAuth is fundamentally a delegation protocol, and that access token gives us a really good handle into our authorization systems, which means that I can still use that token to say this specific token has a set of rights associated with it. It's got a specific user associated with it. It's got all of these scopes. It was issued to a given client. Oh, and by the way, when it shows up, make sure that it has this key associated with it. It also allows me to, if I wanted to with some of these systems, rotate the key when I rotate the token. So splitting these really does make a lot of sense from an information management perspective. So that's out there, and that set of work is something that is kind of mired in the IETF right now, unfortunately, and has been for a very, very long time. We're starting to see it come up again. And again, I'll be touching on this in my afternoon talk with transactional stuff as a different way of looking at this. A little bit newer on the block is the mutual TLS, which got brought up earlier. In this, the client presents a certificate when it goes and talks to the token endpoint. When it goes and makes that back channel call, it presents a certificate. And some of you sitting there nodding might be thinking like, oh, okay, so you're doing mutual authentication. That's how you know which client you're talking to and everything like that. Well, not necessarily. My client may be a public client that's just been dynamically registered or any number of other things. But when I talk to the auth server and I'm in the middle of presenting this code and everything else, that certificate doesn't need to necessarily represent some thing that you know about me, like I got it from a particular CA. It could be self-signed. I could have just generated this. What it represents is that this piece of software can make this TLS call. Like, I'm the only piece of software that should be able to do this. So I can authenticate the client however I like. I can still do Pixie with a public client and still use this. Because what then happens is the AS takes whatever certificate was shown up on the wire there, and it hashes it and associates that hash with the access token. And then the client, when it talks to the resource server, it uses the same certificate to talk to the resource server. Remember, these are all back channel calls. This is not going through the browser interactively. So the client then sends the same mutual TLS to the resource server, and the resource server is not going to do traditional MTLS authentication. So it's not going to necessarily need to go up the chain and validate the whole stack up to the CA, some pre-placed trusted CA. It's not going to have to even associate a specific client with a specific certificate. All that the resource server needs to know is that this token that just showed up is associated with the certificate that was used to present it. So this gives us a very simple and very powerful way to do a proof of key possession with OAuth access tokens. And it doesn't break the rest of the OAuth ecosystem. It breaks the assumptions of mutual TLS, which was designed around presenting the identity of the piece of software with that client certificate. But, that's not really what's happening here, as we see. Excuse me. Okay. Yeah, there is no CN verification. There's no, not necessarily, no.
And can we still kind of lock it down at RS level, saying that, hey, only accept certificates from certain domains?
So the question is, can we still lock it down at the RS to accept things only at a specific domain? Is like, yes, you could. Yeah, you could. The value proposition here, though, is that you can do that lockdown at the authorization server, and your RS never needs to know about that. So your RS, so if you're doing Apache, you configure mod SSL with, it's like no CLA or unverified no CA or something like that as an option, which basically says, take the certificate, make sure that it's actually valid on that chain at the TLS level, and then just accept it and go on with your day. Because the decision of which certificates to accept then gets to happen at the application level, which is what you want. Because what you do not want is a resource server to say, you have a certificate that I trust and you have a token that I trust, but I'm not going to check to see if they're actually associated with each other. Which is what traditional MTLS-based authentication gives you. It's like, you got a certificate. Awesome. Where'd you steal that from? Or you stole it from a different place that you stole the token from. That's great. And, or more importantly, say you're inside of a larger ecosystem and you have a resource server that goes rogue. That resource server's probably going to have an MTLS client cert, or at least be able to get one, because your client developers and everything, you've probably got an issuance process for this. And if they can then take the token that was handed to them and then act as a client to go call somebody else when they're not supposed to, and if all you're doing is checking to make sure that the certificate is part of the domain or has, the right CN or something like that, then you're really screwed and you're not really protecting yourself much beyond bearer tokens. All security systems are only as useful as they actually protect you against these threats. A lot of security systems that we see in the real world, unfortunately, have this artifact of sort of behaving like they're protecting you, but that they're not actually protecting you. And now, oh, yes, before we move on.
So the binding between the token and
That's established at the, so the question is, how do you establish the binding between the token and the key? That happens at the authorization server at its token endpoint when it issues the token. Whatever client certificate showed up at that point on the MTLS layer, it ties the token to that. All right. So now a small requiem for token binding. Token binding, at its core, is a fantastic idea when you have two parties talking to each other. So think about cookies. You're going to say, all right, hey, we're using this specific channel, this specific TLS channel. We're going to establish this. We're talking to each other. This is great. I don't have to send you a client certificate because, especially in a browser, browsers assume that means a user's identity certificate, and that's a big mess. But we're talking TLS, and we can share things over TLS that say, yes, this is really us. And with token binding, the auth server, or whatever website you're talking to, really can say, like, oh, that's great. Keep using this channel, and here's a cookie, but I'm only going to accept this cookie on this TLS channel that we've established. And when you go back, the browser's going to say, like, okay, that's great. Hey, here's my cookie, and I'm still talking to the TLS channel because I'm too dumb to change channels, which is what you want the browser to be. This works really great. However, things start to go sideways in the OAuth world, because OAuth is not a two-party system. And in fact, these are all of the different TLS connections in a typical OAuth deployment. You've got between the browser and the auth server, the browser and the client and the auth server, the client and the resource and the auth server if you're doing introspection. These are all separate TLS channels that have nothing to do with each other because that's how TLS is designed, to keep all of these apart. Token binding in the OAuth world gets a little weird because it basically says, okay, client, you're going to be using it on number 4, but you have to establish via redirects over 2 and 1 and connections on 3 that, trust me, I'm going to be using channel 4 when I use this token in the future, but just believe me, even though we're talking over channel 3. It's doable. It requires a bit of trust to set up, but you can make it work. For me, this requires more machinery than it's really worth because you end up with a lot of moving parts just to get this thing going, whereas with the mutual TLS, it's a lot simpler and makes use of existing technologies, especially once you wrap your head around the fact that I'm tying it to the token and not using TLS as an identity. The other big problem with token binding is that even for the case that it's good for, support has been dropping. Google dropped it from the Chromium project. And Firefox is pretty much said that they're not doing anything with it. Microsoft was doing it with Edge until Edge switched to Chromium. So nuts to that. So token binding was a great idea that's very much in limbo. Kind of sad. All right. So we're going to very quickly, we've got about half an hour left here. Any questions on non-bearer tokens before we kind of burn through this last bit? What's that? Coming back to mutual TLS, yes.
You had AS and RS.
Yes.
So server.
Resource server, yes.
What is the resource server?
The resource server is the protected resource. It's the same thing.
So AS and RS is same.
No. RS is resource server. That is the server that the protected resource lives on. It serves the resource, thus resource server. Yes. Yep. Yes, exactly. Yep. Yeah. One of the problems with the OAuth world is that the terminology is inconsistent at best because it kind of grew up with a bunch of developers arguing about what to name things. Because remember, naming things is hard. Yes. Great question. So is there a way to revoke tokens administratively? That actually feeds into this next discussion. So thank you for the totally not planted segue. In a lot of systems, yes. You go back to the authorization server, and there's going to be a console to do that. But it's only revocable if your resource servers can get that revocation information. Now, we talked a little bit already about the fact that OAuth tokens don't have a format. We're going to look at a way to create a format for a token. And I promise this will tie back to the revocation question. Now, the Jose suite of protocols give you a way to take a JSON payload and without any normalization or canonicalization of that JSON payload, sign it and encrypt it. This is a drastic simplification of classical systems like XML DSIG or even modern alternatives like JSON LD signatures, which require you to take the data, transform it, and serialize it in a very specific way before you can do any cryptographic operations on it. And a JSON Web Token is a way to use those Jose things to protect a common token payload, the kinds of things that you would have in an access token or another security assertion. So you've got fields for who issued the token, who it's targeted to, when it expires, and all of that. So in an OAuth ecosystem, the access token, who would be the issuer of the access token? What do I put in there? The authorization server, absolutely. So who then is the audience of the access token? All right, I heard about an even split mix of resource server and client, and half of you are right. So let's think back to OAuth is a delegation protocol. We are delegating a right of access to the client. However, the client is the piece of software that needs to call the API. So the ultimate destination of that token, and therefore the audience of that token, is in fact the resource server. Because it's the resource server or protected resource that needs to know what that token is good for. The client never needs to look inside the token itself. And there's also this field for an expiration. And this gets back into the revocation question, because if I have a token that tells me what it's good for, it should also tell me when it's not good anymore. So I don't want to have a token that is entirely self-contained that says it is good forever. I do, however, want to protect it. That brings us to JSON Web Signatures, part of the Jose suite. This is a three-part data structure of a header, a payload, and a signature. And that payload can be arbitrary. This, however, is an example of a signed JSON Web Token. Now, look up here. The colors are a little washed out, unfortunately, but if you look really close, you see that it's kind of like that greenish yellow there, and then there's a period. It's about 2/3 of the way through. Do I have it? Oh, I have lasers. Good. Oh, but like you can't see the laser on the thing. That's not helpful. Anyway, sorry, camera guy. So if you go here, all right, this bit is the header. Now, the cool thing about that header is that it looks like gibberish. Take these characters, throw them into a base64 URL decoder. What are you going to get? You're going to get that string, which then very clearly parses as a JSON object. The next section, so follow that all the way down to the next period, that's the payload. And in a JSON Web Token, it's a JSON object. JWS can actually be used to protect arbitrary payloads, including other encoded Jose objects. But with JSON Web Tokens, you get another JSON object there. And this is where we put things about who issued it. Now, we said that the issuer in an OAuth access token is going to be the authorization server. And a lot of times, we're going to represent that with a URL. But JSON Web Tokens don't actually care. As long as whoever is decoding the token recognizes the issuer, we're good to go. Also, this payload is JSON, which means that it is schema by fiat. I can put whatever I want to inside that payload, and as long as the people downstream know what to do with that, it'll be fine. Really, if they don't know what to do with that, it'll still be fine, because as long as it parses as JSON, pretty much every JSON-based data application is just going to ignore the bits that it doesn't care about. That's how JSON works, and that's how developers tend to like it. And then finally, we've got a base64 URL encoded signature at the very end. This is a binary blob. This is not JSON, but it's encoded with base64 URL, just like the other two sections. Which means that if I need to process a signed JOT, It is very simple. I don't even need fancy libraries for getting a cryptographic system right. I can do a string split on a period. That's really easy to do in any language. I do a base64 URL decode on each section. Little trickier, still absolutely doable, very widely available. I'm going to parse the first section as a JSON object. There's my header. That's my cryptographic envelope information. Tells me my key IDs, what type of payload it is, all that stuff. Parse the second section as a JSON object. That's my payload. That's where my application starts to care about things. And then I keep the third section around. I'll base64 decode it, but I will keep it around as a byte array. That's my signature. And why do I do that? Well, how do I validate the signature? In XML dsig and things like that, I would have to then take the payload and then normalize it, probably sort the fields and concatenate them with no spaces and do all of that other stuff. Not so with Jose. With JSON web signatures, I take the raw string as it was sent me across the wire. So that base64 blob with the dots in between it, I take the header, dot, payload. That's my signature input. I don't do any post-processing. I don't parse and then reserialize because JSON is non-deterministic with reserialization without additional rules on top of it. I simply take that string as it was handed to me, feed that into my crypto library, and see if the signature validates. Because I'm going to get what out of my crypto library? I'm going to get a byte array for my signature. Then I see if the byte array that was in the signature field matches the byte array that I get out of the crypto library. And if they do, then I'm happy. I have now avoided having to do any type of normalization or sorting or making sure things are Unicode encoded, or if somebody decided to put backslashes in front of their forward slashes, which JSON weirdly allows but doesn't mandate, then I'm actually all set because they've already given me this. Also, on the other side, generating a signed JOT, really easy. I generate the header object, which is all my envelope information, serialize that as JSON, serialize my payload as JSON, and base64 URL encode both of those and slap them together with a period character. I then take that string and feed it into my signature library with my key. Now this can be an asymmetric key, this can be a symmetric key, this can be elliptical curves. And then I put all of those together, and I base64 URL encode that and put all of those together, and that's how I get my job. Now, you do not need to have a good Jose library in order to parse and even generate these. With that said, though, please use a good Jose library, because there are some corner gotchas, especially about algorithm choice and stuff like that, when you're using this in the real world. That said, though, the underlying simplicity is absolutely in the system's favor. Now, JOTs are very useful because they carry information inside the token. I don't need to go look it up anywhere. And it's very easy to parse and understood with a couple of string commands. And I can get to something that is quote unquote human readable. I mean, I can look at a decoded JOT and figure out that, like, oh, you know what? This is the right issuer, or this is the wrong issuer. I can figure out what's going on there. And because it is not a raw JSON object, it's safe from being parsed and re-encoded on the wire, because part of the rules of processing Jose is that if you parse it and you need to send it again, you need to send the original string. That's understood as part of Jose. So the downsides is that the more you put in the token, the more there is in the token. They can get big. Now, this is orders of magnitude smaller than SAML and other XML-based protocols. It is absolutely staggering, the difference between these. And it's also not directly human readable, especially the payload, which is one of the touted benefits of JSON LD signatures and the like, where you can actually just look at it in a normal JSON parser and you need to do this. But when you get to do the crypto operations on those, you have to then go through a couple of extra steps. And then we are back to our old friend, cache consistency. Because the token is effectively its own data carrier. So if I get a token that shows up and it tells me that it's good for all of these things and it's still valid, and yet in the background an administrator has gone into a console and said, I'm going to revoke that token. I'm over here at the API and I'm parsing this token and I'm looking at it and it tells me it's still good. How am I going to know that it's been revoked? I probably won't, unless I have some other system that tells me that we can do that. Now, you can do that using token introspection, and you can do that using a local lookup if you want to. And there are some guidelines about when it makes sense to use both. Very quickly, highly recommend this tool, jot.io, because it will do the string split and base64 URL decode for you. Ignore their signature processing type of things. Sorry if anybody is here from Auth0 who works on this. Your signature processor sucks. But this tool is immensely useful for parsing the header and payload. I use it constantly. It is very good at that. Also at the bottom of the page, they've got links to a lot of different Jose libraries. Really good resource for the community. I'm not going to get into the details of JSON Web Encryption. It is a 5-part structure instead of a 3-part because encryption is 2 parts more complicated than signing. And that's a crypto joke. But it is out there. There are some good resources out there on how to do that. The keys are where I think things start getting interesting again, because this is a way to get public and private keys across without using certificates. So there's no signing authority. You can host them at HTTPS protected URLs, which means that to get the new key, you just fetch that again and get the keys that are hosted there. It makes rotation very easy. And these are really, really good replacements for where we would traditionally use a lot of self-signed certificates at the application level. Because think about it, what are you really saying with a self-signed certificate? You're saying that I have a key, or I have a key pair, and it's this specific one, and that's all that you care about. Because either you have pre-placed the self-signed public cert on the other side, or you've got some way to do publication, like with the Acme protocol. But with a JSON Web Key, you just get to publish the key itself without pretending that it was signed by Snake Oil Limited, which you then go ignore. So you just take the key and put it as is. Also, it is a JSON object, which means I can extend this with additional information about the key. I can give it an identifier. I can tie it to particular signature algorithms. There's a lot of stuff that I can do with that. Also, one of the other great tricks about this is that this is a private RSA key pair. The way that I make this into a public RSA key pair, well, if I'm dealing with certificates, I have to go run OpenSSL and do the extraction and publish the public cert and all of that, and yada, 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 yada. With JSON Web Keys, I just delete the private key portion from the JSON object. So the D field there is gone. That's the only difference between these two slides. I just made a public-private key pair. Yay! This is a really, really powerful simplification. And there is a tool out there for that as well, makejoc.org. This is now hosted by Authleet. So this is kind of an interesting case where we have competitors in the market space that are hosting community tools because it's good for everybody. So this is a site that will let you go and generate JSON web keys in different formats, and also it has a link to command line tool that you can download locally if you don't want a remote server generating your private keys for some weird reason. Okay, and we are going to wrap up today with identity. Figure I've been talking for 3 hours, I should probably get to the identity part. And also, kudos to all of you for sticking around. There's a lot of good, it's been some great discussion. All right, user authentication. Authentication is all about who the user is, whether they're there right now, and attributes about them, right? So OAuth doesn't give you any of that. We touched on this very briefly earlier. The client has no clue who the user really is. Think in OAuth. Don't add other stuff to it. In OAuth, the client has no idea who the user is. But the authorization server knows who the user is because the user had to log in there in order to approve everything. So maybe we can use that. There's also no way to carry information about the user across the wire, like the auth codes and tokens and everything. Like the client's not reading the token. I mean, maybe we can put it in so the resource server can see it. I don't know, but maybe we can attach this to an API to get identity information because OAuth is about APIs, so maybe. But this last bit, just because I have an access token doesn't mean that the user's still there. For an authentication protocol, I want to have some sort of knowledge about the user's presence. Just because I can get an access token and it works doesn't tell me that somebody's actually logged in. And what that means is that, well, the reason for that is that maybe I used a refresh token. Maybe I used an assertion to get it and the user was never even present, right? So the question here is, can we build authentication using OAuth as a base? OAuth as an authorization and delegation protocol as our base. Can we build authentication on top of that? All right, first try. We're going to say the user is logging into the protected resource. This kind of makes sense. After all, we're protecting it with the login. That feels right. All right, so what does that look like? So on the top, we have the OAuth world. We've got our resource owner, our client, our auth server, and our protected resource. Let's try mapping that to the sign-in world that we're trying to solve. So our user is the resource owner. Great, that's fine. We're good there. Except now we're saying that the user is logging into the protected resource, which we've now taken a server and dragged it out in front of the user and said, this is where you're actually doing your interaction. Think about the OAuth world, though. The user's not interacting with the resource server. They're getting software to do that for them. And so even though we could maybe put some information into that access token and identify the user to the resource server, it doesn't really work because we're crossing that network boundary, that conceptual network boundary, in a way that we really didn't intend to. So that doesn't really work very well. Can we do better? So let's instead say we're logging into the client. Okay, that kind of works because the user is interacting with the client, but hold up. We just said that the client has no idea who the user is in OAuth. It's absolutely true. So this might be problematic too, but let's take a look at what it looks like. So the resource owner is the user. That's great. The client is the relying party, the thing that they're logging into. That makes sense because they're still interacting with it. And if we combine the auth server with a protected resource and what we're protecting is an identity API, we can start calling that an identity provider. Makes sense on this layer that we're using OAuth to protect the identity and the client consumes it, right? So that kind of works. But doesn't that mean that OAuth is an authentication protocol? You guys should already know the answer to this one. No. So I'd like to talk about dessert. Authorization is like chocolate. And credit where it's due, I stole this metaphor from Vittorio, who is also speaking here at Identiverse this week. He has the best hair in all of identity. He does some really good stuff. So this is his metaphor that I've been using for years because it's beautiful. So authorization is like chocolate. It's great on its own. It's also really great, like you can just eat chocolate. You can just use authorization all day. It's also really good as a part of a larger recipe. There's a lot of things you can make with it. You can make chocolate cake, chocolate brownies, chocolate cookies, chocolate fudge. And authentication is more complex. It's a confection that's made up of multiple ingredients, like fudge. Now, usually, like this confection, there is one thing that kind of stands out as the key flavor, which is how you end up with chocolate fudge, or maple fudge, or potato fudge, which every time I give this class, who here has actually had potato fudge, or is it still just me? Dude, yes. You are like the second person to ever raise your hand in this class. Thank you. So it's real. It's actually really good. So anyway, the point here, though, is we're talking about chocolate fudge. You can make fudge using chocolate, but you don't need to. There's a lot of things you can make it out of. Same with a sign-in protocol. You can use it, you can make it using an authorization delegation system as your base, but you don't have to. So let's agree on a recipe for universal chocolate fudge, right? We're going to build on top of a standard authorization protocol and authentication protocol that works across domain. That's effectively all that OpenID Connect is. So the IDP does the various interactive OAuth flows, and then you hand something back alongside the access token that sends information to the client. This is an assertion called the ID token, which is formatted as a JSON web token. But the audience for this is not the protected resource. Remember, the audience for the access token is the resource. It's the resource server. The audience for the login system, though, is the client. So we need a different way to carry that information over, and we're going to do that with a signed assertion, which is called the ID token. We're also going to have a standardized API for dealing with claims and scopes and information and attributes about the user themselves. Now, the parts of an OpenID Connect system should look really familiar. And we've already covered these bits about why you can't use an access token. But this is what an ID token looks like. Should look familiar, right? And pro tip, if you see a string that starts with EYJ0, it probably is a JOT. You want to know why? Base 64 URL decode EYJ0, you get open curly brace, end quote. So it's the start of a compact string of JSON serialization. So the important bits of an ID token are this middle payload, because we've got the header, the payload, and the signature, just like we had before. This is what that payload looks like. We've got issuers, subject, audience, expiration, and an issuance time. The most important bits are these two, the issuer and subject. When you're doing identity with an OpenID Connect system, you take those two together. Those are your universal global identity for your user. Now, is it good enough to just do the subject? No, because if you're ever going to talk to multiple issuers, then they're allowed to reuse the subject. And does that mean the subject is the username? No, because in a lot of cases, you don't want to necessarily leak the username, which might be user chosen, which might be reused, which might be sort of human readable and human facing. You want this to be a stable identifier for the current person's account that only the authorization server can do the mapping. All right? And so these two together, scoped, give us our identity for the user. Now, there's a standard API that I can take my access token and call if I want to get more information about the user. And notice that we've got a subject field here. This has to match the subject field that's in the ID token. You can also get all sorts of other attributes to it, and which attributes you get back are controlled by a set of standardized OAuth scopes. So this is using OAuth to do exactly what it was meant to do in order to get identity information across the wire. All right. Wrapping up, I'll take a couple of questions. We only have a couple minutes. So
is there anything in the spec that's also going to sign the user info?
So the question is about signing the user info. Yes, you are allowed to do that, but the spec is really squirrely about how that is negotiated between the client and server. And so yes, it can, and it basically boils down to just do JOTs. Okay, so Right. So the question is, does OpenID Connect support trust elevation? And sort of, but that's all largely up to the AS to implement it. Yes, you can. So the question is if you can request specific claims and ACRs. Yes, you can do that. That's not the topic today. Yes. Is there a size limit on the JOT token? Not as far as Jose is concerned, but as far as anything that you're trying to cram the token into is concerned, there absolutely is, and unfortunately, that's arbitrary and unknowable. All right. We do need to wrap up here real quick. Last one.
Any recommendations on how often to rotate the JOTs?
How often to rotate the JOTs? It depends on what you're doing with them, and if you have a runtime lookup on that as well. So thank you all very much. This has been great. I'm going to be giving another talk this afternoon about transactional authorization and saying why everything that we're doing in OAuth 2 is wrong and why we should do something else. So please come to that talk. It's going to be a lot of fun. Thank you all.